share my screen. Okay. I think that should be working. We will see. All right. Welcome, everyone. So the activity on last Friday, you kind of learned or / relearned some things about how big O notation works. We also learned about there's this thing called big omega. So I wanted to spend some time talking about those things a little more formally and look at some examples and some additional kinds of things. Now that you hopefully kind of have an intuition from the activity as to how those things work. So, green, I only use green. So asymptotic analysis. So the first question I just want to answer quickly is sort of why? Why do we do this? Right? So why not just, if you want to know how fast an algorithm is, well, just run it and like use a stopwatch. And if you want to know if something else is faster, you just run it and use a stopwatch and see if it's faster, right? So we could always kind of go an entirely empirical route like that. So why bother sort of doing some mathematical analysis to try to figure out, how fast things are or how much memory they take or whatever? So why use analysis and not just sort of an empirical approach? There's a few reasons. One is, it's like a trade-off of, accuracy versus effort. So like, if I have some algorithm I'm contemplating using, if I can do a quick calculation on the back of a napkin and get some idea of how fast it's going to run, right? That's a lot quicker for me than like to implement it, set up a bunch of tests, like run it, gather data, whatever. Also, we want to, I'll say, insulate ourselves from, I'll say, incidental details. Right, like what kinds of, if I actually run an algorithm and time it, what kinds of things can affect how long it takes? Yeah, it's the exact CPU that I'm running it on. I would get different results if I run it on different computers. What else?
The type of language you're using.
Yeah, so the language I implemented in could make a difference depending on like the compiler or whatever. For sure, that makes a big difference. Like whether I also am running, some other program at the same time on my computer because it's going to slow it down, or on alternate Thursdays the computer, like the Wi-Fi goes down and the computer like freaks out and so that slows down. Who knows, right? There's like so many things that could happen. But if we're using some kind of mathematical analysis, just looking at, kind of the idea of the algorithm, then like that stuff doesn't matter. And we don't get as accurate of a result necessarily, but hopefully it's good enough. And to that point, I'll say theoretical efficiency almost always implies practical efficiency. And that's just, you just have to take my word for it. But it just turns out this is a really nice tool that works. And you can imagine some theoretical tools like, well, in theory, this is faster, but in practice, it doesn't behave like that at all. Like, no, actually, most of the time, the theory is going to match up pretty well with practice. So it's a pretty good tool. Okay. Okay, so So let's talk about big O, and I'm gonna give an actually precise definition. You don't need to like know or memorize this definition, but it's nice to see what the precise actual definition is, and hopefully, since you now have some kind of intuitive idea of what it should mean, you can see how the formal definition is working to give us kind of what we want. So informally, right? So informally, if I have some function, f of n is, and on the activity, we were specifically looking at big O of n squared, just to have an example. But of course, n squared could be anything, right? So we'll say it's big O of g of n means, well, what does that mean? Any ideas? How would you, like, based on your experience in data structures or from the activity on Friday, how might you, and I'm going to write maybe a couple different ways of talking about this. So there's not like one right answer I'm looking for. So how would you say informally, like what does it mean that some function f of n is big O of something? Mark?
F of n has a base of g.
A base, what do you mean by a base of g of n?
Like if g of n is n squared, f of n will have some form of parentheses, like the biggest.
Okay, so you said like it's as its biggest thing. Okay, so maybe we could say something like, g of n is the like biggest term of f of n. Right? That's I mean there's more to it than that, of course, but that is a good informal way to think of it. Now, does it have to be like, so for example, if I have 2n squared plus 3, is that O of n squared? Yes, but it doesn't have n squared as its biggest term. It has 2n squared, right? But we don't care about that, right? So, and maybe we can say, up to a constant factor. And what would you all say after the activity on Friday? Why do we not care about constant factors? Or why do we decide that with this notation we're going to ignore those? What would be kind of a justification for that? Mark, what do you think?
Eventually at a big enough input value that it doesn't matter.
That's why I would say that only the biggest term matters. Because eventually for big enough n, the biggest thing it really dominates everything else, right? I don't think that's why I would say we don't care about the constant factors. Because if I have a big n, it's like, well, if it takes twice as long, that's twice as long. Like 5 hours, 6 hours, twice as long as 3 hours. I may care about that in some context. But when we're doing this analysis, why do we kind of ignore the constants?
Because constant factors really only apply when it comes to what computer you're running an algorithm on. And so in order to get rid of what you were saying earlier about incidental details,
right,
it makes sense to get rid of constants.
Exactly. Yeah. Whoops. I keep hitting the erase button. Yeah, that's a good explanation because, yeah, one place that a constant factor would often come from is you run on different computers. It might take 3 times as long over here, or maybe half as long over here, and we want to analyze things at a level that is not specific to a particular computer. So twice as fast, half as fast, doesn't really matter. I mean, it can matter in some circumstances, right? But if it really matters, then this is not an appropriate tool to use. We could also say something like, eventually, and this was like one of the definitions on your activity. We'll say f of n grows at a similar rate. A similar or smaller rate as g of n. And so this is one thing I hope you got from the activity. Usually, like in data structures, we just use big O to mean that things grow at this rate. Technically, really, big O means it grows at that rate or a smaller rate. It's like less than or equal to. There is something that means exactly at the same rate, and we'll see what that is. So, I guess we'd have to change this a little bit. Say, well, it's the biggest term, or the biggest term is smaller, whatever. I mean, we're just being informal. So, all right. So let's see a formal definition. So I'll say formally. So we'll say f of n is big O of g of n if and only if, well, there exists some constant c greater than 0. So this is the like we don't care about, if it's a half or 2 or whatever. That's what the c is going to be. And some n0, and this is the eventually part. And we'll see that in a second. Let me just finish writing this, and then we'll talk about the different pieces of it. Such that for all n greater than or equal to n0, f of n is less than or equal to c times g of n. Okay, so this isn't saying it has to be true for all n, right? It says there's some n0 such that once you get past that point, then this is going to be true. We don't really care what happens before that point. So this is corresponding to the word eventually. So eventually, once you get past n0, then f of n is always going to be less than or equal to some constant times g of n. But in particular, this constant doesn't change. As n keeps getting bigger, the constant is always the same. So f of n is always less than or equal to, say, 2 times g of n, or something like that. Or a half, or 5, doesn't matter. Okay, so I'll draw a little picture. So maybe like here's here's our g of n. Or maybe this is like, let's say this is like 2 times g of n, for example, right? And maybe f of n looks like this. I don't know. Kind of a bad drawing, but you get the point. It doesn't matter. So this is our, this is our n0. Doesn't matter what happens before that point, but from this point on, f of n is always less than or equal to 2 times g of n, right? Or it could, it could go like, oops. It could go like this, right? That's certainly less than 2 times g of n, so. All right, well, what questions do you have about this definition? Gary?
Does C need to be an integer?
No. Some real, just any real number. N0, I mean, I guess n implicitly, we're assuming n is, usually we're talking about integers, but actually the definition doesn't really care. We just usually care about integers because usually the functions we're talking about, the input is like the size of some input, and it's going to be, you can't have like 10.5 bits or something. It's like the size is an integer. But the definition works perfectly well if n could be a real number. So it doesn't matter. Good. What other questions?
So why do we use a constant for c when we drop? I guess it's just to account for like n squared versus like 2n squared. Like if you were to like calculate the time for an algorithm, right?
Yeah, I mean if you're an algorithm that takes n squared, time proportional, or an algorithm that takes exactly n squared versus an algorithm that takes exactly 2n squared. I mean, clearly one is twice as fast, but up to if we're talking about big O, we don't care about the difference between them, right? They're both O of n squared. Because like you run them on a different computer and they would behave the same or.
Is there a proof for this?
A proof. This is a definition. So I mean,
no.
We can define it however we want. There's nothing to prove. It's just like it just happens to be a useful thing to give a name to. And partly you could just take my word for that, but partly I hope that because of the intuition we've built up, you can kind of see what the different parts of this definition are doing. In particular, right, the C is building in this idea that we don't care about running our algorithms on different computers. And this N0 is building in the idea that we kind of only care what happens when N starts to get really big. When it's small, we don't really care what happens, right? Because, if I have some algorithm, or let's say I have some problem I need to solve. If I'm solving it on 10 things, it really doesn't matter what algorithm I use. And pretty much any algorithm I use, it's going to be pretty much instantaneous because I only have 10 things to process. I could just do it by hand, right? But if I have a million things, now it starts to matter more whether I use an algorithm that takes some time proportional to n squared or n, right? So for example, a good rule of thumb is that when you write a computer program, it can do about 10 to the 8 operations per second. It's a decent rule of thumb. So that's 100 million. So if I have a million things, and I do an O of n algorithm, right? That should run in like 100th of a second. It's going to be very fast. And it really doesn't matter if it's like 20n. Okay, fine. It's 20 hundredths of like a fifth of a second. That's still like pretty much right away. But if it's an O of n squared algorithm, right? A million squared is what? A trillion, 10 to the 12th. And so if I can do 10 to the 8th things per second, that's 10 to the 4th seconds, which is what, 10,000 seconds? That's, I don't know, that's hours. And again, it doesn't really matter if it's a half or 10 times that or whatever. It's going to be hours versus a second. And that makes a huge difference, right? And it doesn't really matter. The constants don't matter. It's just the fact that I can say, look, this algorithm is going to be something like O of n, and this is going to be something like O of n squared. If I run it on a million things, I can say this is going to take seconds, this is going to take hours. And it doesn't really matter exactly how many hours or exactly how many seconds. I don't want to wait hours. All right. Any other questions? All right. And so hopefully, here's a couple examples. 3n squared plus 7n, minus 12 is, we could say this is big O of n squared, right? And if I wanted to, I could like formally apply the definition, and I could say, okay, well, my C, I guess I have to pick C to be 3, or 5 would work, I guess. And I don't know what the N0 should be. I mean, you'd have to, well, no, actually C, well, I don't know if C could be 3 because it's always going to be like plus this 7n, so it'll be like a little bigger than 3n squared. So maybe 4 would work. And I would have to find an N0 that's big enough. Like, it's tedious. I'm never going to ask you to like actually precisely apply this definition. Our intuition is going to work, and also we'll see it probably in a minute. There's some things we can do if you're comfortable with limits. There's some things we can do with limits to make this to give us some nice ideas of what things are. But we can also just look and say, look, clearly the biggest term is this term, 3n squared. I don't care about the 3, so it's O of x squared. Right? Or as another example, like, 17n squared plus n times the square root of n, minus the log of n. I know that's some crazy stuff, but like n squared is still going to grow faster than these things. And we'll spend some time thinking about how fast different things grow relative to other things. So, if you aren't sure right now whether these, like, which is the biggest term, that's okay. We'll spend some time talking about that. Okay. One thing to point out, right? Like this thing, for example, it's also O of n cubed, right? Because big O really is like less than or equal to. So anything that's bigger than this is going to be a valid thing to say. It's maybe not the most useful thing to say because it's not a very tight bound, but it's true. Say etc. Okay. So here's a question for you. How would I change this? How do you think I would change this definition to make it into a definition of big omega instead of big O?
You would flip the f of, you change it from less than or equal to greater than or equal to for the line f of n is greater than or equal to c times g of n.
Right. Exactly. That's all. So if I flip this less than or equal to a greater than or equal to, that's the definition of big O. Or big omega, excuse me. So I'll say if we flip to greater than or equal to gives the definition of big omega. And we're going to be careful in this class to use things like big O, big omega, and some other things we're going to talk about precisely. And like, why do we care? Why do we want both? Because there's situations where we might want to talk about an upper bound to something and a lower bound to something because maybe they're not the same. So a great example is matrix multiplication. So if you have two n by n matrices and you want to multiply them, how long does it take? It turns out we can easily say it takes O of n cubed time because you can just write some nested loops. There's a very obvious way to write some nested loops, like 3 nested loops, and do it. And you're like, okay, clearly I can do it in O of n cubed. We can also say it has to be big omega of n squared because the output is going to be an n by n matrix, and I have to at least like write every one of those n squared entries, and so it's going to take at least that long. And the question is like, can I do it faster than n cubed, or like where like? And it turns out we do know actually that it can be done in big O of n to the 2.37 something something, but like there's a gap and no one actually knows like. Is there like some? Is it can actually be done in O of n squared time? Is there like some limit where you can't do it faster than a certain thing? Like we don't know. So it's useful to be able to talk about lower bounds and upper bounds separately, in cases where you don't know precisely how fast something can be done, or maybe we have an algorithm and it's so complicated we can't even say precisely how long it takes. Okay. So definition. But when we do know precisely how long something takes, or how much memory it uses, or whatever, if f of n is both O of g of n and big omega of g of n, right? This was like that, the part in the middle on the Venn diagram on your activity, right? Then we say that f of n is big theta of g of n. So this is big theta. Right. And in LaTeX, it's backslash theta. Okay, and we'll use that precisely too. So for example, this 3n squared plus 7n minus 12, this is big theta of n squared. Like n squared is precisely the rate at which it grows up to a constant. It's definitely not theta of n cubed, right? It's O of n cubed, but it's not big omega of n cubed, so it's not theta. So right, I guess what I was saying before is a lot of the times, like in data structures and in general, people often use big O. They throw on big O as if they're talking about big theta. And in an informal context, that's fine. So if you're just like talking to someone, you know, at your job, and they're like, "Oh, this algorithm, it's O of n squared," right? Probably what they mean is big theta. In this class, we're going to be precise, but in the real world, usually people just talk about big O. But it's going to be useful for us to be more precise. Let's see. See how much time I have. So let me. Yeah, here. So I said, like, sometimes we can just look at things, be like, well, I can just look at this and tell that it's 12n squared. And that's fine. But for more complicated things, it'd be very tedious to apply this definition exactly, right? Because it's very tedious to try to find a C and find an N0 that work, and then to show that they actually work. Right? So there's a much easier way that we can do things. If you remember your calculus, and I'm guessing most of you have taken calculus, we technically recently removed the calculus requirement from the major. So in theory, you don't have to, but I think most of you probably still have taken it. So I'm not going to prove this theorem. It's kind of tedious to prove, but it's not conceptually difficult, right? And the idea is, if I look back at this picture, right, what we're really talking about is kind of in the limit as n goes to infinity, what happens to like how fn and gn relate. And in particular, right, if I want to look at like fn divided by gn, if I divide both sides of this by gn, you know, I want that to be like a constant or something. I want that limit to exist, basically. So, theorem, if I'll say 0 is less than or equal to, the limit as n goes to infinity of fn over gn, and I'll just write less than infinity, which is not really valid, but we know what that means. It means the limit doesn't diverge. It like converges to some constant. Then f of n is big O of gn. Right, so think about this. Like, if the limit is 0, that means that as n goes to infinity, like gn gets a lot bigger than fn. Right, and so in that case, fn is going to be like smaller than gn. Or if the limit is some constant, if the limit is say 2, well, that means they're growing at exactly the same rate, but you know, with a difference of a factor of 2. If the limit goes to infinity, that means that fn is growing faster than gn, and so it's not big O. Okay, and then we can say, well, what if, you know, 0 is less than, so the limit is not 0. I'm going to put less than or equal to infinity, which again, totally bogus notation, but what we mean is, well, the limit, it could be some constant, Could be like 2 or 6, or it could diverge. The limit could go to infinity. Right. Then it's big omega. Right, because again, we don't want the limit to be 0 in this case, because that means Fn is much smaller than Gn, or it's growing much more slowly than Gn. But as long as if the limit is a constant, that means they're at the same rate. Or if the limit is infinity, that means Fn is growing faster than G of n. So it's big omega. It's like growing faster than or equal to G of n. And as you might expect, if the limit is a constant, if it's not 0 and it's not infinity, then it's big theta. Any questions about this? We'll see a few examples of this, but this is definitely a useful tool that we have to think about whether something is big O or big omega or big theta or something else in cases where it's not immediately obvious. And it's much, much more convenient than trying to apply the definition, because this, you just don't have to worry about any of those constants or n0 or anything. You're just like, well, what's the limit? You're like, oh, it's a half. Great, done. And I will extend this, and this is actually not a theorem, this is a definition. But it like fits into this whole thing. So if 0 equals the limit, then f of n is, we call this little o of G of n.
So always less than.
Yeah, so this means, right, if the limit is 0, what does that mean? Well, that means G of n is growing much faster than Fn. As n goes to infinity, this gets smaller and smaller and smaller, right? Which means that Fn is like truly growing at a smaller rate than G of n. And this is a useful thing to say. For example, you might say, I need to find an algorithm that is little o of n squared. What does that mean? That means you're not satisfied with n squared. You want something that's truly faster than that, right? And not like a half of n squared or a tenth of n squared, like n, for example, or n log n or something like that. Right, so little o f of n grows strictly slower than G of n. Okay.
So is there like a little theta that represents like strictly bigger than?
Yeah, it's little omega.
Yeah.
Yeah.
Little.
Yeah, there is, and people use that. I mean, so you use a lowercase omega, if you know what that looks like. But we're not really going to use that in this class, so I'm not going to mention it. But yes, that does exist, and people use it. Is there another question? Yeah.
I assume that those are just not going to come up since it would involve being like negative inputs, which doesn't make sense. But like, if there was a square root in this equation, that would potentially like lead to negative values or at least the implication of the values that just would not matter for this.
You mean like if one of these functions involved a square root or something?
Yeah.
Yeah, it could, and yeah, because we're pretty much only ever going to be concerned about positive values or non-negative values of n, because n typically for us is going to be like the size of an input, and it doesn't make sense to talk about negative sizes, right? And so yes, square roots can occur, and we will in fact see some algorithms that feature square roots in terms of how long they take. probably haven't seen that before, but there do exist such things. Yeah, I think sometimes like a common misconception, you come out of data structures, you're like, well, everything is either like it's O of 1 or it's O of log n or it's O of n, or there's like this weird n log n thing and there's n squared, and like that's it. Those are the options, right? So we're going to see lots of weird things that don't fall into any of those. I mean, those are very common, but yeah, we'll see other things. Yeah.
Are there any algorithms that take like big O of 1 over n?
1 over n. Oh. So that would mean that it gets faster the bigger the input is?
Yes.
No. I don't know how you could actually get faster the bigger the input is. Because at some point, if you keep getting faster, it means you can't even be looking at the whole input, because if you're even just looking at all the input, then you at least have to take O of n time, right? And even things that don't look at the whole input, like log of n algorithms, like binary search, for example, can ignore parts of the input, but it's still getting slower the bigger the input. I would just, at that point, I would just say it's O of 1, because you could just bound it. If it's always getting smaller, you could just bound it by whatever the longest is that it takes, or like the smallest input, and then just say it's bounded by that. So it's O of 1. That's an interesting question. All right. So what I want to do for the rest of the time, we've got maybe like 10 minutes. I'm going to start, and I think probably I'm maybe going to make like reworking things a little bit. I might make a new activity for you all to do on Friday that continues what we're going to start now. But we've seen all the definitions. I just want to like look at a bunch of examples. Like we'll go through kind of some common like I mentioned, you see commonly like, theta of 1 or theta of log n or n squared. So we'll like talk about some of those common asymptotic complexities that we'll see, and we'll talk about some examples that you all know of at this point. And also maybe along the way prove some things about how things relate to each other. So I'll call this is our asymptotic complexity zoo. So first is theta of 1, which you could also say O of 1. When you're talking about a constant, theta versus big O doesn't really matter, because anything that takes time less than or equal to a constant is just got to be a constant. So so this is constant time. And again, most of the time, when we're using this notation, we're talking about time. But you could also talk about how much memory something uses, or how big something gets. But we will often talk about time. So, right, this is just something that does not depend. Or I'll just say constant. I won't say constant time. Does not depend on the size of the input. So, for example, access a given array index. Right, and we all know, like, if you have some kind of list or array, like a list in Python or an array in Java, and you like say, list bracket whatever, we can immediately access that thing. We don't have to like scan through the whole list to find it. And of course, the reason that works, like you've probably seen this if you've taken CSO, for example, is that we allocate the array in consecutive things in memory, and then when you want to access a certain index, you can do some math to figure out exactly where it is. You just go right there and you get it. You don't have to like search there. What else takes constant time?
Arithmetic.
Yeah, so we usually assume that like doing an arithmetic operation takes constant time. Usually, we'll see some things in this class where if you're starting to talk about like doing arithmetic on really big numbers, that stops being true, and you have to think about how big the numbers are. But like if you're just talking about doing arithmetic on numbers that are represented in like registers on a machine, right? They're bounded by a certain size, so we can just say, yeah, it's constant time. What else takes constant time or constant space or whatever? Zoe?
Like appending something?
Yeah, so like appending to, yeah, appending, usually, yeah, a lot of things appending to like a list or usually takes constant time. And actually, there's you might put a little asterisk next to it. There's like some interesting stuff going on, how that works, but we'll talk about that. We'll talk about that later. Also, like usually we think of like hash table operations. Again, big fat asterisk next to it, but essentially we can think of like inserting or removing from a hash table making constant time. There's other things, but those are a good. So the next one I'm going to talk about is theta of log n. So this is logarithmic. And by the way, you know how like ln is natural log? It's like log base e. Right? Well, lg is log base 2. That's a common abbreviation for log base 2 specifically.
Oh.
And in this class, as you can imagine, like pretty much every time that we talk about a log, we're going to mean log base 2. Because the way that logs are going to come up for us is when we're like repeatedly cutting things in half. Because that's a very, very common thing, algorithmic thing to do. And but it turns out it doesn't matter. So we'll say note that, right, so like if I have log base, a of x, there's this change of base formula. I don't care whether you remember this formula or not, you're not going to need it, but it's the same as log base b of x divided by log base b of a. I think, something like that. The point is, notice this is log a of x is equal to log b of x times 1 over this. And what is this? It's a constant. Okay, I mean, who knows? It depends on what b and a are, but the log base b of a, it's some number, and we don't care. So this is a constant, right? Hence, what do we conclude? If we're talking about big O or big theta, we don't care about the base of the log. It doesn't make a difference. The only difference it makes is a constant factor. So like theta of log base a of x, or n, I'll say n. I guess I should have used n up there. Equals theta of log base b of n. The base doesn't matter. Okay, so that's why you might see people write like, O of log n, log, or O of lgn, or, whatever, but it doesn't matter. It doesn't matter what the base is. What are some things that take logarithmic time or space?
Binary search tree.
Yeah, so if you like doing a lookup in a balanced Binary search tree. Yep. What else? Some of these things you'll saw on homework 0, right? Like binary search.
Merge sort.
Well, merge sort doesn't take log n time; it takes n log n time.
Oh yeah.
Yeah. You know, like the depth of a balanced binary tree. That was one of the things on the homework, right? And that's why lookup in a balanced binary search tree takes log n time, because you'd have to go down through the depth, right? That's also why, for example, inserting in a binary heap takes log n time, because you might have to go up the spine of the tree. Log n is also like the number of bits needed to represent n. Right, so if I want a number n in binary, I need log n, theta of log n bits. Yeah, Gary.
Yeah, right, because it's the logarithm of the inverse of exponents, and
right.
In bits we need 2 to the n, so it's...
Exactly. Yeah, logarithm is inverse of exponent. So I hope, if you only come away from this class with a few things, this is one of the things I hope you come away with is a much more comfortable and intuitive sense for logarithms. So it's actually really a shame that usually you see logarithms first in the context of calculus, because the way that logarithms come up in calculus is really not intuitive. It's like, well, it's this certain limit of something, and you're just like, and it's the antiderivative of 1 over x, and you're just like, what is this thing, right? And there's all these weird rules. But logarithms are really, they show up really naturally, right? It's anytime that you're like repeatedly dividing something by a constant, like you're going half and half and half and half, and it's like, how many times do you have to do that before you get down to 1? Because it's the inverse of exponentiating. Exponentiating is like you're like doubling. Logarithm is like half. It is cool the way that they connect to calculus and stuff like that, but it's not, in my opinion, it's a confusing first way to see them, because it doesn't really give you a good sense of what they're for, like why you would, where they would come from. Okay, well, I think we're out of time, so we will pick this up. I'll let you know before class whether we're going to be in here or over the other side, but we will pick this up next time. Mason?
Sorry for being late.
Sorry.
I didn't send an email about it.
Okay.
Okay. It's fine. Yeah, there's just a fire alarm thing.
Oh yeah. And I forget who. Someone mentioned that they said you might be late. So yeah.
So is there anything I needed to keep track of besides the lecture notes and the homework?
You mean in terms of? Hang on a second.